One type of graph that you're going to have to be able to read is a potential energy graph. So let's look at it before we look at some of the questions. Here we have two hydrogen atoms and they're too far apart. So as you go left to right, you have the internuclear distance. So basically bond length. Then as you go up and down, this is energy. So this one has to do with bond strength. As you move the two hydrogens closer together, as we move the hydrogen atoms closer together, they start attracting and they become more stable. But eventually, they're going to get too close to each other and then the nuclei are going to start repelling. So the forces in hand, we have electron to electron repulsion, nucleus to nucleus repulsion, and then you have electron to nucleus attraction. These are the attraction and repulsions that are going on. So let's look at the questions. When two hydrogen atoms are very far apart, the potential energy approaches what value? Well, here, two hydrogens are very far apart, and it approaches 0. As the hydrogen atoms move closer together, their potential energy starts to decrease. As the potential energy decreases, the strength of the bond increases. When the distance between the two hydrogen atoms becomes less than 0.74 angstroms, or 74 picometers, the potential energy is going to, so as it gets smaller, our potential energy is increasing. Because of if they're getting too close, they're going to be because of repulsion. So it's going to take a lot of energy to keep getting them closer and closer because they're going to repel each other. So we're trying to find the happy spot between attraction and repulsion. The observed bond length is the distance at which the blank forces between unlike charges. So if it's between unlike charges, it should be the attractive forces, which would be between the electrons and the nuclei, are balanced by the blank forces between the like charges. That would be repulsion. And that would be between the electron-electron and nucleus-nucleus. The lower the valley is in the graph, so this valley here, the stronger the bond. This is showing how much energy is needed to break the bond. Basically, what's happening is this amount of energy, whatever that corresponds to, that's how much energy was released when that bond was formed. So that's how much energy would have to be put into the bond to break it again. Go ahead and pause the video and answer these two questions about these two molecules. We have the one that's represented with blue and green. So the first question, which molecule has the longest bond length? Remember, bond length had to do with the x-axis. So the longest bond length would have its valley the farthest to the right. So that would be the green one. Then, which molecule would require the most energy to break the bond? That one's going to be the one with the valley. The one with the valley lower. So that would be the blue line. So whichever molecule is represented by the blue. So So we're going to shift over to ionic bonding. Ionic bonding occurs between two ions, and it's formed when electrons are transferred. They're held together tightly, and therefore they have high melting points. We'll talk more about properties of ionic and covalent in our next unit. So as a reminder, we've talked about isoelectronic ions, but if you've forgotten, these are ions containing the same number of electrons. So all of these ions have 10 electrons. The more negative, the larger the ion due to a smaller nuclear charge. This one is the most negative. It only has 8 protons and 10 electrons. So it's the largest compared to aluminum, which has 13 protons and 10 electrons. So it would be the smallest. More protons to electrons are going to pull in the electrons, making it smaller. This one has very few protons to pull in the electrons, making it very large. So for these two, go ahead and figure out who's the largest ion in each group. Make sure they're isoelectronic before figuring out the largest. Restart when you have your answers. So for A, lithium ion has the same number of electrons as helium. Neon. Potassium has the same as argon. Rubidium as krypton, and cesium as xenon. These are not isoelectronic, so then I just look at this set, and xenon is the largest. So cesium plus 1 must be the largest of that set. For part B, barium ion, it has the same number as xenon, 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 and xenon. So these are isoelectronic. Therefore, the most negative, or tellurium -2, would be the largest. So the new piece is lattice energy. Lattice energy is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. K is a proportionality constant. So the ones that we're more concerned with are Q. Q1 and 2 are the charges on ions. So what's the positive charge and what's the negative charge? And we're going to multiply them together. And then R is the distance between the center of the ions, aka the radius. For a large or exothermic lattice energy, in other words, a great attraction between the ions, we're going to want two things. So make sure you're writing these down. The first thing you always look at is charges. The greater the charges, the stronger or more exothermic the lattice energy is going to be. If the charges are the same, and only if the charges are the same, you're going to look at radius. Because radius is on the bottom, we want a small radius. So smaller ion sizes. So let's see what that means. For each of these 4 sets, you're going to figure out who has the highest lattice energy. That can also be worded as the more exothermic lattice energy. So the first thing I would look at is my charges. Magnesium is a +2 charge. Chlorine is a -1. Sodium is a +1, and chlorine is a -1. I'm going to multiply them together. 2 times 1 is 2. You can do the absolute value of that. So I'm not doing +2 times -1. I can just say 2 times 1, and then 1 times 1 is 1. Because magnesium chloride has the larger charges, it would have a greater attraction for each other. So magnesium chloride would be the answer. Go ahead and pause the video and do B, C, and D on your own. Restart when you have your answers. So for B, you should have seen that all the charges were the same. So we couldn't look at charges. We wanted the smaller radius. Well, bromine is the same in both of them. So you were just looking at cesium versus potassium. Well, potassium is smaller, therefore it had the higher lattice energy. For C, aluminum had a greater charge than magnesium, so it had the higher lattice energy. And for the last one, we didn't know the charge of lead, but we could figure it out by knowing that sulfur is a -2, so lead must have been a +2. Copper, we didn't know, but we knew chlorine was a -1 and there was 2, so copper had to be at 2. So based on that, PBS had the higher charge. Go ahead and pause the video, figure out which one would require more energy to overcome the ionic bonds, and explain. You will need to explain sometimes, and you need to bring it back to that lattice energy. So first, of these two, aluminum has a greater charge than magnesium, so it must be the one that requires more energy to overcome. So when you're writing out your answer, make sure that you start with the actual answer. So aluminum oxide has a greater lattice energy because aluminum ion, so this is an ion, has a greater charge, which is a +3, than magnesium ion, which has a +2. So then, what does that greater charge mean? It means that aluminum ion would have a greater attraction to that oxide ion, requiring more energy to overcome the ionic bond. Make sure that you have all of this in your answer, and pause the video if you need to make sure that you get it all written down.